I am Craig Rizian. I work at Oregon State University. I'm a faculty research assistant in the College of Earth, Ocean and Atmospheric Sciences. We have new college names and always get stuck on that. Still getting used to it. So I'm in the Coastal Oceanography group here in CEOS, and primarily my job is working on two ocean observing programs. One is called the Ocean Observatories Initiative, which is a National Science Foundation funded program the second program is a IOOS. It's a NOAA IOOS, so the National Oceanic and Atmospheric Administration. They've funded this Integrated Ocean Observing System program, and that program is made up of 11 regional associations distributed throughout the country, and I work for NANOOS, which is the Northwest Association of Networked Ocean Observing Systems. Oceanography is full of acronyms. There are millions of acronyms. So basically I work for NOAA IOOS and this NSF OOI project, just to round out the acronyms. My role within certainly the NANOOS program is I work on a lot of data, creating data visualizations. We work on this tool, this platform called the NANOOS Visualization System. So what we do is we try and bring together many different types of data, model forecasts, much like the atmospheric model forecasts that you see on TV. We try to bring all of this information from various disparate federal agencies, state agencies, universities, etc. together, and we make that information available through a Google Map interface. So I'm involved with that project. Again, that's an NANOOS visualization system. And then I'm also a technician. So our college is full of technicians, and we fulfill an important role where we tend to be the ones who build buoys that collect a lot of the ocean data that you see. So that means everything from bolting foam together, pieces of foam together onto some sort of metal platform, building anchors and painting the buoy with anti-foulant paint, to building battery packs, data loggers, getting data loggers, cell phone modems, all the sensors together and wiring it all up so that we can log all of the information and then telemeter, so transfer that information to shore. And that is done through various ways, but primarily the buoy that I work on, which is called NH10, and that stands for the Newport Hydrographic Line, and its location is 10 miles west of Newport. We use a cell phone modem, and we collect information on that buoy, conductivity or salinity information, temperature, dissolved oxygen, wind speed, barometric pressure, that sort of thing. We log all of that information, and then we telemeter it back to shore, where I'm responsible for processing it, so checking the data, quality control, quality assurance, QA, QC type work, and then pushing that data to, for example, the National Data Buoy Center, which is a federal part of it's a federal department. I don't know exactly, but it's part of NOAA, and they then distribute the data nationally. So it's part of what I do for NANOOS. For the Ocean Observatories Initiative, it's a relatively new program. We're right now kind of towards the end of the planning phase, and we're moving into the deployment phase in 2013 this year, and then 2014, 2015. It's a very large National Science Foundation project, about $400 million, and it consists of 4 global nodes. These are how to define a node. These are places that we've identified off of Greenland, in the middle of the North Pacific, off Chile and Argentina, where we will be deploying a series of buoys and a profiler, which is a very sophisticated buoy that goes up and down through the water column, as well as gliders, these underwater autonomous vehicles, for a year at a time, and then we'll go back and recover that stuff and put some new gear out. And we'll do that for 25 years. And there are also 2 coastal arrays here off of Oregon and Washington, and off of the East Coast. And we'll be, again, deploying moorings, buoys, these profiling systems, and gliders. And lastly, it comprises of this regional scale node, which is a cable observatory that goes out to Axial Seamount and Hydrate Ridge, and that it's run by the University of Washington, and it will be it was deployed over the last couple of years, and the sensors and buoys and things associated with that array will be deployed starting this year with the actual sensors. So the cable went in, various cable parts and primary infrastructure. I'm not going to try and describe that over the last couple of years. And yeah, we'll be deploying that, starting with the deployments for all of that equipment this year. So that's a very exciting project. The gliders are, they're buoyancy driven, and there's different types of gliders. The ones that we will be using for OOI are called Slocum gliders. They're made by Teledyne Web, and these fly. They've got wings, and they use buoyancy, and basically what happens is they surface, and using Iridium satellite connections, we're able to communicate with the glider, download data, and send it commands. And once it has its commands, it will start to dive, and there are no propellers or anything. It's just buoyancy driven. It's got these wings, and it will actually dive down to, well, if it's, depending on the glider, if say it's a 200-meter glider, and you're in 80 meters of water, it'll sense the bottom, and then it'll turn and come back up to the surface. If it's deeper, if it's down at 200, it'll sense that it's at depth and return to the surface. And while it's gliding through the water, it collects salinity information, dissolved oxygen, temperature, current velocity information, so it can tell some of the, it can sense using ADCPs, acoustic Doppler current profilers, what the current velocities are.
So
it's,
it'll be taking data as it goes down through the different
yes,
density layers and,
yes,
and
it will,
back up.
yes.
So it'll have a depth as well as all these other
it gives you a profile
kind of, I mean, is it kind of three-dimensional in a way, the data that you would get out of it, or is it a path?
It is along the path. It's three-dimensional if you look at it in time, because
Right,
it's
if you
moving
get
around.
multiple,
Yes,
right.
and with multiple profiles you would get more of a three-dimensional view of the ocean. A lot of these data are used, talking about trying to get a three-dimensional or even a four-dimensional, so latitude, longitude, depth, and time view of the ocean. A lot of these data are assimilated, so they're incorporated into ocean models to help improve the accuracy of those models. And people here at OSU have been trying to include glider data as part of that modeling process, and then using this assimilated data that improves the predictions, they're able to generate forecasts. So we're actually able to forecast ocean conditions now 24 hour and 48 hours in advance, which is something pretty new and novel.
So can you talk a little bit more about modeling, about what, so your data can help the models, what does that mean, and what does a model do? If you want, you don't have to.
I'm going to start kidding myself. I'm not. I'm going to go on record and say I'm not a modeler. So these are numerical models. The atmospheric models that you see on TV, those are simplified to create a view that's more easily digestible, than when you see the numbers, the actual these huge arrays of numbers that come out of these models. But basically, it's a bunch of equations, and you run them through a computer, and it comes up based on laws of physics and how we, our understanding of the ocean and the atmosphere, and how circulation, how things circulate, how there's flux transfers, there's energy transfers. There are all these sort of things, and so you try and parameterize the model based on this understanding. And then you run it through a computer, and the computer comes out with an answer. So it'll say, well, based on these initial conditions and the physics as I understand it, and the resolution, which is important, the time resolution and the space resolution, so how fine are your your squares in your model. This is what I think the forecast for tomorrow will look like. And so we do that for the atmosphere all the time, and we're all comfortable with where the forecast is saying it's an 80% chance of rain tomorrow. And we've been doing that for the atmosphere probably, I don't know, decades. The ocean forecasting is a lot newer, and so it's not as advanced as the atmospheric forecasting, but it's the same idea where it's a computer simulation of what the ocean may look like tomorrow based on these parameters and this understanding of the physics. And so what having data is critical to ocean modeling, because like I said, it can help improve the model's accuracy. If you incorporate all of this data into your model, it can sort of push it towards a more realistic result. But it's also having these data sets. Part of what these ocean observing systems are doing is they're building up these long time records. And so what we can do going forward is we can take these records and we can do model data comparisons, and we can start to look at how the models are doing. So over the past decade or so, we've started generating these predictions for climate change. So there's an estimate that whatever the temperature will rise 4 degrees over the next 100 years. And we make all these model predictions, and these are numerical models, these computer simulations. And once we have these long time records, we can then go back and we can say, okay, those models said X, and the data, how do the data fit to those model forecasts? And so that sort of work is really important. And having the observations is really important to helping us improve the models and better understand how the models work and how they're doing in terms of making these predictions, whether it's weather predictions, which is short term, tomorrow, 2 days from now, or there's long-term climate predictions. The data that these observing systems are collecting is really critical to both of those fields. The obvious one that comes to mind is climate change, but and that's critical and that's really important. It's kind of been beaten to death. That's the thing that people really talk about. One of the new things, well, it's part of climate change. One of the new things that people are really starting to talk about, there's in the past there's been a lot of discussion of sea level rise, which is important and something that we should be concerned about. Warming temperatures in the atmosphere, melting ice, these sorts of things. But one of the newer things that people are really starting to look at, and people are growing rather concerned about, is ocean acidification. And so as we pump more CO2 into the atmosphere and that enters the ocean, the oceans are becoming more acidic. And we're starting to see some real problems for industries such as the shellfish growing industry along the Oregon and Washington coasts, where they've seen year after year failures, and basically this acidic water is coming into their systems where they're growing these oysters and things, and they're seeing it's not a crop failure, I don't know what it is, but they're harvest failures essentially. So they're and so some of the Whiskey Creek hatchery, for example, along Memphis and Oregon and Washington. But anyway, they're partnering with people here in the college in CEOS to try and understand this issue more, and they're now collecting near real-time information. So they've actually set up sensors, data loggers in their hatchery, and we at Nanus have partnered with these guys. So we actually ingest their data and make their data available, but they're looking at this information and trying to make decisions as to when they should flush their tanks based on atmospheric conditions and ocean conditions, to minimize the impact that this acidic water, because it changes with time. There's a temporal component to it, so Burke Hales and George Walbus are trying to work on this problem, and with the these hatchery owners, to try and minimize the impact that this corrosive water is having on their stocks. So it's a component of climate change. It's if you look at the model forecasts, it's paints a rather grim picture going forward, and it's something that we're really this ocean acidification. We're seeing the impacts today, and it's impacting shellfish growers right here locally in Oregon and Washington, impacting their bottom line. And the forecasts are that it's going to get worse. And obviously, other things will then be affected, like coral reefs and these sorts of things, which are already battling with increasing sea surface temperatures, which can result in coral bleaching. Having these reefs exposed to increasingly acidic water is also going to be a huge problem. Yeah, and one of the things that isn't often talked about with regard to these ocean observing and efforts, whether it's NOAA, IU's or NSF's OOI project, is the engineering that goes into the various projects. So these gliders, from an engineering standpoint, they're very cool, and they're obviously being improved all the time. And whether it's software engineering or the hardware, trying to design these things. For example, the OOI specifications and requirements are that gliders for the global arrays need to go out for 1 year. That's a long time for a glider to be out there. And for us, we're going to be deploying these things for 2 to 3 months. And in the past, they've been deployed for 3 weeks, maybe 4 weeks at most, I think. So, there are a whole lot of design changes there to meet the requirements for OOI, meet our requirements. So, the profiling systems, that's a very new technology, and there's a lot of design and engineering that goes into that. And the profilers that we'll be using here off of Oregon, they're going to be supplied by one company. I don't yet know exactly what that is, because we had an RFP on the street, and it's all secret. But the University of Washington, they'll be designing and building their own profiling system, the Applied Physics Lab. And then we've got another one, which is Rolls-Royce, actually. The Bedford Institute for Oceanography in Canada built this thing called the Sea Cycler, which is this huge, it's about the size of a VW bus. It's an enormous thing. And that'll be deployed on the global arrays. And Rolls-Royce bought that. And so we're going to be buying some of those for the global arrays. So there's very cool ocean engineering, software engineering work that goes into all of this stuff. From our basic little moorings like NH10, we did a little bit of engineering and things. We redesigned it this winter. Unfortunately, it's still broke. We've lost it. We don't know where it is. So we'll have to go back to the drawing board on that one. To the Ocean Observatories Initiative, which is a whole different ballgame, which, $385 million to build it all, and then there's $55 million a year to maintain it for 25 years, which is very different to the IU's budget, where Nanus gets $1.7 million a year. So, and that's divided up amongst many people. So it's the Ocean Observatories initiative. The scale of it is just tremendous. It's amazing, and the engineering that's going into it is pretty incredible too. The ocean is very inaccessible, and it's very corrosive, and it's a very hostile environment, which is part of the challenge and what makes this sort of work interesting. I mean, it's hard to get there by ship. You have to be out there for weeks at a time. Salt water doesn't work well with electronics. 40, 50-foot waves smashing. That's, I think, well, we know that's what killed our mooring this past winter. It got hit with 35-foot waves for 12 hours. And we lost it in mid-November, and the last couple of days we've got visual confirmation that it's not there. So, it's just an extremely hostile environment, and OOI is pushing the envelope in terms of trying to deploy things, for example, in 25 meters of water. So, when you've got 40-foot waves, 30-foot waves coming through in 25 meters of water, that's a very, very difficult environment to maintain your hardware, your buoy. So there's going to be there's more engineering challenges in trying to harden these systems, trying to reduce the buoyancy, so when the waves get really, really big, they kind of go underwater and hide. These sorts of problems are being looked at, and various engineers at the various partner organizations. So it's Woods Hole, Scripps Institute, University of Washington, Oregon State University, what engineers at these various institutions are trying to figure out how to do. And then all of that's tied together through this very advanced cyber infrastructure that the University of California at San Diego is responsible for. There's computer science stuff going on too, where UCSD is trying to figure out ways to communicate with sensors that are deployed in the Southern Ocean to change their sampling, or get back a status to try and understand if something's going wrong, what could be going wrong, trying to automate the QA, QC, the quality control, quality assurance of these data, to reduce the number of humans required, these sorts of things. So, to the gliders, telling them to dive, to change course. If there's an event and there's an eddy, an ocean eddy, and you want to go and sample the eddy, to be able to have that command and control to send the glider off and go and sample that eddy. So there's the software engineering side very much so, which is critical to this